Hey everyone, I'm Michael Unger, the program coordinator here at the H.R. McMillan Space Center. If you've ever come into the building before, you may have noticed the shape of the building. Some people think it looks like a UFO, others a hide-a-hat. And that's a good reminder, because this building, built in 1968, was built on the unceded territory of the Musqueam, the Squamish, and the Tsleil-Waututh nations. In front of the building, you'll notice that there's a large crab sculpture that was placed here in 1968 by George Norris. And the crab has two meanings. One, the crab is a symbol of the zodiac, Cancer. But also, the First Nations people believed that the crab was a protector of the inlet. Looks pretty cool, doesn't it? Hey everyone, welcome to Cosmic Nights. How's everyone doing? Thank you so much for joining us. We hope you are staying safe, staying informed. This is an incredibly turbulent time in the world. There's the time of exposed systematic racism and injustice. And you know, as scientists and as educators, we want to make the world a better place. And sometimes we struggle with what the right thing to do is. And as an organization, we're still trying to figure out how we're going to address some of these issues that are happening in the world right now. But I can tell you that we are going to have those conversations as an organization, and we also like to have them with you as well. And I'm so glad that you've joined us here. We are dedicated to help elevate and support this conversation. And it's nights like tonight, Cosmic Nights, were always very special nights for me because they were a place of gathering. And we could gather together, and of course we can't all be face to face right now, but we get to delve in deep and have really interesting conversations. And so tonight we have a fascinating one. We have black holes, which of course I think are probably the most fascinating objects in the universe, some of the most mysterious as well. That's why they're called black holes. And we have a really cool program for you set up for about the next hour. And here's how it's going to go. We've got two special guests, which I will introduce in a few seconds. But of course, as you can see, we're in Zoom. So this is a bit of an experiment. And it's really cool that we can gather in here, and hopefully we can facilitate some really good conversation in here too. So there's two ways that you can interact with us. You can have a chat. You can basically talk with other people and hopefully keep that chat respectable. But if you want to ask questions, especially for our special guests a little bit later on, you should use the Q&A feature. So you see there's a Q&A feature there. And another really cool thing about the Q&A feature is that you can upvote other questions. So if you see a question that somebody else has asked and you really want that question answered, you can upvote that one. And then, of course, we're going to do a little bit of polling, have some fun in here. Yeah, like I said, this is our first time doing this Zoom experiment. We've usually went from Zoom to YouTube. And of course, there are people out there perhaps watching on Telus Optic. Hello to you all out there. Unfortunately, if you are watching Telus Optic, you won't be able to interact with us, but maybe next time. So let's bring in some of our special guests. So first up, my trusted colleague who I have not seen in months. I miss her dearly. And that is our local astronomer, Rachel Wang. Hey, Rachel, how's it going?
Hi, it's going well. I'm excited to be here, talk about black holes.
I know I'm getting kind of tired of just seeing your face on the computer screen. It'd be nice to be back in the planetarium, hopefully soon. But yeah, black holes. How are you feeling about this subject?
Very excited. You know, these are one of the most exotic objects that we have in space. And I really love that because, you know, you don't get that here on Earth. There's no way that you can run experiments to that kind of magnitude and that kind of intensity that you do have in black holes. So I'm very excited to talk about them today.
Awesome. So a little bit later on, Rachel, you're going to give us a look at sort of like a preview to sort of like the preview to black holes, which is the life cycle of stars, which leads us to black holes. And then after your presentation, we are going to get to our featured talk tonight. And I'm super excited to bring it all the way over from the other side of the country, staying up late. But, you know, as astronomers, that's what we do. We like to stay up late. So let's bring in Nathalie Ouellette, who is a coordinator for the Institute Research on Exoplanets. It's a long title, but that's why they call you IREX for short, right?
That's right, yeah.
It's a cool title. You are the coordinator at IREX, which is out of the University of Montreal, and you're also an outreach scientist for the James Webb Space Telescope, which I can see by the necklace hanging around your neck. You are a James Webb fan.
That's right.
Welcome, Nathalie. Nice to see you.
Hi, nice to see you too. It's too bad that we couldn't see each other in person this year during some of our conferences, but this is the next best thing for now.
Yeah, I think this is really a fun and interesting time now that we get to do these digital events that we get to reach out to people like you across the country.
That's right. You've been hounding me for like a year to do one of your events, and I've never just happened to be in Vancouver.
I know.
Now I can just pop online.
I think you still should come to Vancouver.
I agree. Next year.
Yeah, so a little bit later on, Nathalie, you are going to give us our featured presentation all about black holes. And of course, that is related to James Webb in a bit, and maybe questions about James Webb will come up. So let's, since this is, you know, a social gathering, we have, let's see, over 105 people that have joined us in Zoom. We'll probably get a little bit more a little bit later on. Let's get our first poll of the night, because of course, at Cosmic Nights, we like to have a little bit of fun, and of course we like to have some beverages as well. So put into the chat what everyone is drinking tonight. Of course, I am obsessed with my soda stream, so I've got some soda water.
That's what I did too. I don't have my soda stream bottle, but I put it in a glass.
But rest assured, I've got a nice dark matter beer waiting for me after this event is over. What about you, Rachel? What do you got drinking over there?
I've got some nice H2O.
As anyone should, as we're speaking, because I can feel my mouth already starting to get parched. This happens when I'm home all the time and I'm not like having conversations in person, and then all of a sudden I'm like on the computer and I'm having like my first real conversation. My mouth is not ready for it. So we've still got some responses coming in, but let's end it now at a minute, and let's share the results here. And it looks like other is the
So
winner.
cryptic.
I guess we can only speculate what other may be. So let's all speculate. Nathalie, what do you think? What do you think other is?
Soda, like not soda water, like
pop?
Coke. Yeah, pop. Yeah, that's right.
What about you, Rachel?
I was thinking like a cocktail or a spritzer, something in between beer and wine.
Okay, yeah, I'm gonna go with a scotch, and of course,
Nice.
if you want to put into the chat what you think or what you actually are, is that a float? What did somebody say here? Ice cream.
Ice cream. Melted ice cream.
Melted ice cream. So we'll do some polls throughout the rest of the night. It'll be fun. It'll be a little bit of quizzing, that sort of stuff. We also had a bit of an activity that we sent out to all of you. Hopefully you had a chance to see our, we usually have like activities for people to do, a question prompt. What do you think a black hole would look like? Of course, we do have a photograph of a black hole. We're going to talk about that a little bit later. But of course, we are looking for people to be artistic to see what they can come up with. And then, of course, the question asked, what do you think we should call our Milky Way black hole? Now, a little bit later on, we're going to talk with Daryl Haggard. We're not going to hear about Daryl in our chat tonight, but it's going to be the bonus coverage that we're going to send to you on a YouTube link. And Daryl Haggard worked on the Event Horizon telescope, and she told me a really cool name, but you're going to have to watch the video to find out the really cool name that some of her and her colleagues are calling our Milky Way black hole. So, for Nathalie and Rachel, let's have a bit of a quick little roundtable chat about the misconceptions around black holes. Now, Nathalie, I know that you are an outreach scientist. You're out there talking with the public, and Rachel, of course, every day. When people are coming to you and talking about black holes, what are those common misconceptions people are talking about? We'll start with you, Nathalie.
Sure. The first one, and I'm getting it less and less, so I think we're doing a good job, is people just think that black holes are like really evil vacuum cleaners who are out to get you specifically. And they're rather docile creatures as long as you give them space. So I'll talk a little bit about that, but they're not out to get you, and they're not like chasing after you. They're not vacuum cleaners.
Yeah. Rachel, what about yourself? What kind of questions are you getting?
I get one from kids a lot where they're asking whether or not black holes are really black in color. And that's always kind of a difficult one to explain to kids, because I'm like, yes, if you're going to draw a black hole, you would definitely use a black marker. But then there's an argument from Hawking that there's Hawking radiation, that these black holes do emit thermal radiation in forms of heat or light. So they really aren't all that black, as Stephen Hawking said in his words.
And you know what? We've already had an upvoted question, 13 people, which we might as well knock it off. This is great. Before we get into it, which is really quite simply, what is the closest black hole to us? And proper answers only. We're going to keep it respectable. Nathalie, Rachel, either one of you tackle that one?
Sure. So this actually changed, not the actual black hole, but our knowledge of this changed just a few weeks ago. Up until recently, we knew of a black hole something like 6,000 light years away, quite a bit away. We know that there are most likely hundreds of millions of black holes inside of our galaxy, but they're really hard to observe. We only have observed like a dozen or so of them. But recently, we spotted one that was just 1,000 light years away. It's in a triple star system. So there were two visible stars and the one black hole. And we knew about the two stars for a long time, but then we started studying their orbits a little bit more closely. And we realized, well, wait a second, there's like something else going on there. And we realized that one of the stars is orbiting something invisible with a period of 40 days. And then we realized, oh, there's a black hole right there, 1,000 light years away from us.
Nice. That's great. We were able to knock out some of those questions. We're going to get to pretty much near the later on portion. We're going to have lots of questions, but we're going to do one more because before we get into, Rachel, your first talk, I'm going to show a video all about the James Webb Space Telescope. But a great question that's been upvoted, which I think is a good one. Who is James Webb? Nathalie, you want to tackle that one?
Sure. James Webb was the administrator of NASA during the Apollo missions. So he wasn't an astronomer, but he was someone who gave a huge contribution to space exploration in general. So he was around during the Apollo missions, including the really famous Apollo 11, where you had the first steps on the moon. So he was a very important figure in space exploration, and NASA tends to try to name their space telescopes after important figures in astronomy.
Awesome. And maybe we'll get a little bit deeper into some of the science that James Webb is going to do. But before we transition, Rachel, you're going to give our presentation on the life cycle of stars. But let's take a quick little break. Let's re-up on our beverages, and we're going to watch a quick little video here from NASA all about the James Webb Space Telescope. Hey everyone, I'm Michael Unger. All right. And of course, the James Webb Space Telescope is going to be kind of like the replacement for Hubble. And it's certainly going to give us a much deeper appreciation of the universe. And as Rachel, you're going to tell us all about, a deeper appreciation for all of the stars that we have out there. So why don't we hand things over to you, Rachel, for our first presentation of the night, the life cycle of stars.
Sure, thank you. So I'm just loading up my software. It's the same software that we use in a planetarium. So I'll remind you that even though it looks like a circle, it's different than the usual rectangular view that you're used to, but it is the same software that we would project onto the dome at our planetarium, where we have Harold in the center. I do miss Harold, but fortunately, I do have the ability to share with you the same visuals that we have there. So Michael, let me know if you see the Orion Nebula on the center of your screen.
Yep, we're good to go.
Awesome. So I thought I would walk us through the life cycle of stars. So stars start off born in stellar nurseries called nebulae, a giant cloud of interstellar gas and dust, much like this one, which is the Orion Nebula. Now, the evolution of a star, or what a star will end up as, is completely determined by its initial mass, or how much matter is available in its nebula. Now, around 4.5 billion years ago, waves of energy traveling through space pressed these clouds of gas and dust closer and closer together, until gravity caused them to collapse in on themselves and start to spin. Now, as the gas spins faster and faster, it starts to heat up and flatten just like a pancake, and eventually gathers enough mass in the center to form a protostar, or a baby star. Now here is our sun as a young protostar, a ball of hydrogen and helium not yet powered by fusion, with the orbits of hypothetical planets shown here in blue to give a sense of scale. Because remember, the planets haven't formed yet. Now, eventually, over the course of millions of years, the temperature reached 100 million degrees Celsius, which is hot enough for nuclear fusion in the cloud's core. So this is what our sun looks like now. The star will burn its hydrogen fuel in the fusion process until that fuel runs out. And at this stage, the star is in a stable equilibrium because nuclear fusion provides an outwards pressure that supports against the inward pull of gravity. Now, we call stars like these main sequence stars, and our sun is actually a great example of one. Now, when the hydrogen supply in the core starts to run out, the star can no longer generate heat and outward pressure through nuclear fusion, and the core becomes unstable and actually contracts. Now, the outer shell of the star, which is still mostly hydrogen, starts to expand, as you just saw happening here. And as it expands, it begins to cool and glow red. The star is now in what we call the red giant phase, and our own sun is actually about halfway through its lifetime and will reach this phase in about 5 billion years, expanding all the way out to the orbit of Mars. Now, after the outer layers have expanded, over the next few tens of thousands of years, the star will eventually radiate away this outer layer, and over time, it'll do that through solar winds. Now, stars with 1 to 5 times the mass of the sun, which is representative of about 97% of the stars in the Milky Way, will leave behind a much smaller dense core called a white dwarf. Now, white dwarfs are no longer undergoing nuclear fusion, so they'll start cooling over a long period of time. The star's low temperature means it'll no longer emit significant radiation in the form of heat or light, and it'll become a cold black dwarf. But because the length of time it takes for a white dwarf to reach this state is actually calculated to be longer than the current age of the universe, it's thought that no black dwarfs quite yet exist. Now, what about more massive stars? Well, if you have stars that are around 5 times the mass of our sun, after the red giant phase, they'll undergo a fast core collapse. The inward pressure of all that collapsing material is so great that a huge rebound explosion happens, and the star's material is spewed out into space in a violent explosion, and that's called a supernova. Now, supernovae are brighter than their host galaxy when observed, and we see on average 1 supernova per galaxy every 50 years. But what's left behind after the supernova? Well, stars that are initially more than 8 times the mass of our sun will leave behind a neutron star. Now, neutron stars are these extremely dense objects that are about 10 kilometers across and can have the mass of 1 to 3 suns squished inside. That's like squishing 1 to 3 suns in somewhere the size of Vancouver. Now, neutron stars are the densest objects in the universe. So 1 teaspoon of neutron star material weighs about 15 moons placed on the Earth's surface, or about 900 times the mass of the Great Pyramid of Giza. Now, sometimes, as the white dwarf collapses to form a neutron star, it gains a lot of spin or angular momentum in the process, and you end up with a rapidly rotating neutron star, also called a pulsar. Now, beams of radiation pour out in huge jets along the magnetic field lines at the poles. The fastest pulsar recorded was found to rotate around 716 times per second. Now, when we study pulsars from Earth, every time one of these jets passes us, it counts as a blip in our data. Now, lastly, if the star is more than 15 to 20 times the mass of our sun or more, after its white dwarf stage, it'll form a black hole. Now, don't let the name fool you. A black hole is anything but empty space. Rather, it's a huge amount of matter packed into a very small volume. You can make a black hole by squeezing a star 10 times the mass of a sun into a sphere the size of Calgary. And the result is a gravitational field so strong that nothing, not even light, can escape. And that brings us to the end of the life cycles of stars of different starting masses. This goes to show that not all stars will end up as black holes. Instead, what they end up as is completely determined from the beginning, when the stars are just forming in their stellar nurseries or in their nebulae. And Michael, I'll throw it back to you as I stop sharing my screen so you can bring it back and start a little bit of a Q&A.
Yeah. We're going to cancel your spotlight. Thanks, Rachel. That was awesome. Let's throw up a little bit of a poll here. I got to bring back my video. There we go. And we forgot to bring up the first poll, but we'll do it here now.
Sure.
And we'll see if people were listening. This will be sort of like our little test for the night. And of course, if you have any questions for Rachel, put them into the Q&A. Let's see what we got here. Ooh, we got some good ones here. Lots on black holes. We'll maybe save those for Nathalie. Anything on the life cycle of stars? Now, of course, talk a little bit about neutron stars a bit more, Rachel. Like, how are we able, I think I'm always fascinated by this, how are we able to measure sort of like how massive a star could be? Like, how do we get those measurements?
Sure. That answer comes from really from relativity, talking about how matter tells space-time how to curve, and the warpage or the curvature of space-time tells matter how to move, right? So we can look at how extremely dense objects like neutron stars are affecting the orbits of other things passing by. Just like Nathalie was talking about how we knew that there was a 2 stars in a triple star system, and we just so happened to find that based on the gravitational variations that there was another object there, and that was extremely, extremely dense.
Yeah. And awesome, and 51% of everyone was listening to you, Rachel. So that's great. Densest objects in the world. So let's do another one. Stop sharing. These polls are just so fun to do. So you did talk about supernovae.
Mm-hmm.
And of course, earlier this year, we were talking about Betelgeuse, which was potentially going to go supernovae, right?
Yes.
Could you maybe tell us a little bit about the story about what was going on with Betelgeuse?
Sure. So Betelgeuse is a variable star. So really what that means is that we are expecting it to vary in brightness. But what was peculiar about its behavior last year was that it was reaching a historical minimum in its brightness. So it's the dimmest it's ever been before. So astronomers were kind of looking at it and being like, well, it's doing something a little weird and a little bit out of the ordinary as to what we were expecting it to do. So with Betelgeuse coming closer and closer to perhaps maybe going supernova, that timeline is really, it could go off tomorrow, it could go off in the next 100,000 years or so. But I think that astronomers are really just hopeful that something would happen, because seeing a supernova like Betelgeuse in our lifetime would be very, very cool. It'd be as bright as a full moon and would cast shadows on Earth. So it was very exciting, the prospect of it going supernova, but unfortunately it doesn't look like it'll happen.
Right. So would that have been the one that potentially the one supernova that we could have seen in our galaxy?
Yeah, exactly. So that's why we were all so amped for it.
Awesome. And of course, everyone, we've got a whole bunch of spillover people that are watching on YouTube. You can also, I'm also monitoring the chat over there. We do have supernovas and about the speed of them. So how fast does a supernova happen? Is it like immediate, or is it over the course of like days? You know, of course, like if you're talking about the supernova, you're talking about the actual explosion. I guess there's different processes of the supernova, but do we know sort of like how quickly that happens?
Right. So of course it does take light to travel to us. So if a star like Betelgeuse did go off, we would have to wait for that light travel time before we would be able to see the actual supernova happening. But the actual process of the explosion is really fast. There is some mechanism in which that the supernova does stall a little bit and has to be revived. So it takes, it's very, very quick, but it's not as quick as you might think it would be.
Great. Another question that comes in, mostly focusing on the star questions. We're going to save all the black hole stuff for Nathalie later. Christine asked, what stage is our sun in?
So our sun is on what we call a main sequence. And it's really this really useful diagram called the Hertzsprung-Russell diagram, or the HR diagram, that astronomers use to plot spectral class, or like the color or temperature of a star, against how bright it is, or its luminosity. And it happens to fit right in the middle, kind of on a diagonal. We call that the main sequence. And a lot of stars end up on the main sequence, just like our sun is. And our sun is halfway through its lifetime. So it's on its way to that red giant phase, where it'll expand and eject its outer shell of hydrogen. So that's in quite a few years, 5 billion years.
So we're okay for now, right?
We're okay for now. Hopefully
we've got enough. We've got enough problems that we're trying to deal with right now. We don't want the sun to be another one.
Yeah, exactly.
This is a really cool question. I like this one. What was the life cycle of the very first stars?
Ooh, the very first stars.
Good one, Dave.
Oh, I actually don't know this one. I don't know if Nathalie would know about, I believe they're called population 1 stars, the first stars that were born. And James Webb will help us look for that. So Nathalie, I'll throw that one to you, actually.
I think because astronomers are really weird and like to count backwards and stuff, they're actually called population 3. Population 1 is the youngest. I think
nothing's ever straightforward.
I know, right? Like our brightness scale is like backwards and like not linear. Anyways, population 3 stars were actually really big, like bigger, heavier, more massive than the bigger stars that we have now. And so they had incredibly short lifespans. And what is interesting with them is that they were very pure, because a lot of the elements that we have around us, anything beyond iron, has to be created in a supernova explosion or like the collision of neutron stars or something like that. And because they were the first stars around, they didn't have any of those elements to populate themselves. All they had were the elements that were created by the Big Bang, which is hydrogen, helium, a little bit of lithium and beryllium. And then they had to like produce the heavier elements within themselves up to iron. So they were very, very pure, very massive stars with short lifespans.
That's amazing. Thanks for jumping in there, Natalie. I think that's
No
a great
problem.
segue into black holes. I'm going to throw up another little fun poll, though, because we're going to transition into talking about black holes. And a question that I thought would be fun to ask is, what do you think is going to happen inside of a black hole? So your options are nothing. Is there nothing inside of a black hole? Is there a wormhole to another dimension, maybe another universe? Is there a tesseract? I guess we're talking about aliens. The Disney version, if anyone's seen Disney's The Black Hole, apparently hell is on the other side of the black hole. Or is it all the matter and stuff that the black hole has ever consumed in its lifetime? Is it all packed down in there? Or maybe other? We're going to give you a chance to keep asking that, and we're going to watch a cool little video here about the picture that we took and where that black hole is that we took a picture of, and then we'll talk a little bit about it. So of course, that is the black hole picture that I'm sure most of you saw last year. And that was taken by the Event Horizon telescopes. And like I teased out earlier, Daryl Haggard from McGill University, also in Montreal, she was part of that project. And I did an interview with her that we're going to share with you at the end of this presentation. But Natalie, why don't you quickly tell us a little bit about, as you segue into your presentation about the Event Horizon Telescope.
Sure. Well, I do talk about it in my presentation
Sure.
with like visuals,
Okay.
which is more interesting than my face.
Well, hold off then. Let's quickly go to the poll results. What is inside of a black hole? Wow, 63% say all the matter and stuff that a black hole is consumed in its lifetime. What do you think about this, Natalie?
I think that is a very intellectual, pragmatic answer.
What do you think is inside of a black hole?
What do I think is inside of a black hole? My scientific mind thinks that, but my science fiction mind thinks something else, and that'll be something else that I'll talk about in my presentation.
All right. Well, without further ado, let's get to your presentation.
All right.
All about black holes not sucking.
Okay. You can see my screen?
You can.
Perfect. Okay, so thank you so much for having me. Thank you, Rachel, for talking about the life cycle of stars. Usually I start with that, but then I don't have to. I will show a few images though, because you have like really cool planetarium software, but I'll show a few images that were taken with real telescopes. So this is a planetary nebula. This is what is going to happen at the end of the life cycle of our sun. So like an average size star. Here you have the outer layers of the star that have been blown off. And at the very center in the circle there, you have the leftover, the white dwarf that we mentioned. But this is an average size star. So most stars will end up that route. But we are interested in black holes now, and that requires a massive star. Massive stars have very interesting lives even before their deaths. Here you have a type of star, a massive star called a Wolf-Rayet, and you can already see that it's very, very active. It's blowing off material into its environment. It is way more intense than any kind of solar storm that we can see in our solar system. You can see the size of the star there at the center, and then what's going on the outside. You can actually take a real picture of all of that stuff that's being blown off. And then at the end of the life cycle of this type of star, you get a supernova. And supernova explosions are some of the most powerful phenomena in our entire universe. We can see them, even though it's just a singular star, from very, very far away. And in fact, when a supernova explosion happens, the brightness of that one star is as high, as bright as all of the stars in the galaxy, the other stars combined together. So it's a really, really bright, violent, energetic phenomenon. And at the end, you end up again with a nebula, but another type of nebula. And at the center of this nebula, which is sort of like the leftover of the explosion, you have a black hole. Here, you can't see it the way that you would with a white dwarf or a neutron star, but you can still see its effects. And I'll talk a little bit about that. So a black hole, we have to not really look at it directly unless we have very special tools like the Event Horizon Telescope, but we mostly have to try and see the effect that it has on its environment, and that is related to space-time. So Rachel mentioned space-time a little bit, and it's related to mass. So whenever something has mass, it will warp space-time. So here you have a star, say the sun, and it is a mass that is weighing down and deforming space-time. Space-time being the three physical dimensions, spatial dimensions around you, but also the dimension of time. So I like to say to someone, well, space-time is basically, if you want to meet your friend somewhere, you need to give them 4 coordinates, 3 coordinates in space, 1 coordinate in time. So that is the fabric of space-time all around us. And so the larger the mass is, the more it deforms space-time. And this is how you end up with objects like planets being caught in the gravitational field of stars, essentially. So we had a little animation of something like a star trapping a planet in its gravitational field, but the heavier and denser your object, the more it deforms space-time. So here you have a diagram, you have the sun, it deforms it a little bit. You have a neutron star, which Rachel mentioned, and it is much, much denser than the sun, so it deforms it even more. And a black hole is even denser still, and that deforms it extremely, extremely a lot. A big distortion in space-time. So what's interesting when you deform space-time, I mentioned that a planet can sort of get caught up in an orbit around a mass that's deforming space-time. But at some point, you could theoretically escape from that orbit. If we were able to strap gigantic jetpacks on the Earth and give it a velocity, a speed, some energy in the opposite direction from the sun, we'd be able to escape the sort of divot, the deformation that is being created by the sun. But the deeper you are in that hole, the harder it is to get out. So if you are trapped in the gravitational field of a black hole, at some point, you hit a certain depth in that hole where you would have to go faster than the fastest thing in the universe, faster than the speed of light in order to get out. Which is why there is a region around the black hole called the event horizon, where if you are within that region, you cannot get out. So this is like the danger zone, essentially. If you're within that region, even if you're going faster than the speed of light, you are still stuck within the area of influence of a black hole. So you asked me, Michael, what I think is inside of a black hole. And I think, yes, it's true that if you're inside of a black hole, you're falling in. It's basically just all the matter and all of the stuff that's been accumulated by the black hole. But if you're interested in something a little bit more fantastical in science fiction, Event Horizon makes me think of one of my favorite movies, which is Event Horizon. It's a movie from the late 1990s, and it has everything that I love. It has space, it has horror, and it has one of my favorite actors, Sam Neill. And essentially, they're thinking that you can basically play around with black holes and end up in a dimension that is very hell-like. So it's not the Disney version of hell, it's a much more intense, gory version of hell. If you're interested in space, science fiction, and horror, I strongly recommend you watch Event Horizon. So trying to actually look at black holes is very difficult, as I mentioned, because they trap everything around them, including light. So the reason why we can see things in space is because they're able to radiate light or reflect light. The reason why we can see things around us here on Earth is because light is being bounced off of objects or being emitted by objects and then entering our eye so we can observe them. But if you had a black hole in front of you and you try to shine a light on it, the light will be basically trapped inside the event horizon of the black hole, which is why it appears black. But because it has such a strong gravitational effect, you actually can see some very interesting distortions around the black hole. So if you have something behind the black hole that is shining light, and all of the light rays are like moving out radially from that object, they won't be able to pass right through the black hole. They'll try to like pass next to it, but the gravitational field will actually bend that light and cause a phenomenon called gravitational lensing. So theoretically, if you could get close enough to a black hole to see what's going on, you would have a strange optical effect like this. But it's not really observing the black hole directly, it's observing its effect on its environment. One thing that I like to ask, and it's especially interesting to ask when I have presentations to kids, is what do you think would happen if we replaced our sun with a black hole? So here you have a little animation, you have the sun, all the planets that are orbiting around it, and then say spontaneously you replace the sun with a black hole, exactly the same mass. What would happen? Would all of the planets fall into the black hole like it was a giant vacuum cleaner? Would all the planets be kicked out, or would nothing happen? And a lot of children, because of science fiction still answer all of the planets are going to be sucked in. Over the last decade or so, 12 years where I've been doing public outreach, I've actually had a higher and higher proportion of children answer that the planets are going to stay put, which is sort of like very good news to me. That means that science fiction is starting to sort of change the way that they portray black holes. So in fact, a black hole spontaneously appearing in the place of the sun that had exactly the same mass as the sun would not change the orbits of the planets. Gravity doesn't really care about what is making up a certain mass. It just cares how much mass is there. Obviously, there would be different effects. We wouldn't have sunlight anymore, and that would not be good for life on Earth. But gravitationally speaking, all the planets would stay put because exactly the same mass would be there. So this is proof that black holes are not these evil monsters that are just sort of sucking everything that's close by. You have to be close enough to a black hole in order to fall into it. So there are different sizes of black holes. We've mostly been talking about stellar mass black holes. They're created at the end of the life cycle of a very massive star. But we also know of supermassive black holes that live at the hearts of galaxies. And to get from a stellar mass black hole to a supermassive black hole, there are intermediate steps. And the intermediate black hole is actually still quite a mystery because it is a necessary step to get from the small Legos to the bigger, supermassive black holes at the center of galaxies. But we don't actually observe that many intermediate sized black holes. These are sort of like 60, 100 times the size of the sun, essentially. So we have a bunch of different missions who are hoping to observe some of these intermediate sized black holes that can explain a little bit better how the supermassive ones at the hearts of galaxies are created. But now I'll talk a little bit about supermassive black holes, which are of a particular interest to me because I am very interested in how galaxies evolve, how they form. And because supermassive black holes are such huge components of galaxies, we have to consider them when we talk about galaxy evolution. So just to sort of place ourselves in the setting here, we are in a galaxy. We're in the Milky Way. It's a spiral galaxy. Our sun is about 2/3 of the way out in a spiral arm. And at the heart of our galaxy, a few decades ago, we were starting to be able to look at the motion of individual stars that orbit the center of our galaxy. So this is a little diagram that shows the movement of these stars. So you can see the epoch, so the date when these observations were taken, and you can actually see how these stars are orbiting relatively quickly around nothing. So there was no luminous visible object that all these stars were orbiting around, which was very, very odd, but they were orbiting around something that was calculated to be 4 million times the mass of the sun. So this is when we realized that there was a black hole that was way more massive than what we would expect from simply the end of the life of a massive star, right embedded in the heart of our own Milky Way. So this is what we call Sagittarius A star, or asterisk, and this is our supermassive black hole at the center of our galaxy. And we think that the great majority of galaxies, especially larger galaxies, have supermassive black holes at their heart. Ours is pretty well behaved. It's not very active, but some galaxies have really, really active black holes that are actively feeding on material. And sometimes you can actually get jets that are being shot out of the supermassive black holes at the center of these galaxies that are pretty much the entire size of the galaxy. So this is one galaxy called Centaurus A, and you have, you can see sort of a dust lane passing through more horizontally, and that is about the size of the galaxy, about 100,000 light years across. And in the other direction, sort of more vertically, you have polar jets that are shooting out of the supermassive black hole at the center of that galaxy. So this is pouring an immense amount of energy into the galaxy, and this actually stops stars from being able to form inside of a galaxy. So an active supermassive black hole at the heart of a galaxy can actually cut off the formation of stars and sort of kill a galaxy. So this is why it's super important to study these types of phenomena, because they affect how galaxies evolve. So we have one, most galaxies have one, and we would love to see a supermassive black hole, but we actually need very, very special instruments to do this. We need a telescope, but not any kind of telescope. We need a telescope the size of the Earth, because the larger your telescope, the more resolution you have. Essentially, the sharper your images can be, and the more definition you can get with images that would be otherwise like very, very small, or two objects that are very close together. You need to be able to have a huge telescope in order to take this kind of observation. Now, we don't have a telescope that is the size of the Earth, unfortunately. But what we can do is build telescopes all across the Earth and have them coordinate together in order to act like one big telescope. So this is what the Event Horizon Telescope is. It's not actually one single telescope. It's a network of 8 different radio telescopes that are in a bunch of different countries all over the globe that are able to work together, coordinate together to take an image of a supermassive black hole. And they were able to do this for the first time. And this image was released a little over a year ago now, April of last year. And this was the image that was released. It's not the supermassive black hole at the center of our galaxy. It's instead the supermassive black hole at the center of a galaxy that is very near and dear to my heart. It's called M87, and it is one of the most massive galaxies in a group of galaxies called the Virgo cluster. So I mentioned that our supermassive black hole is 4 million times the size of the sun. This one is 6 billion times the size of the sun, so much bigger. This galaxy is bigger than our Milky Way. This supermassive black hole is bigger and more massive than Sagittarius A. So what is in this picture here? A lot of people, when they first saw it, if they don't know too much about astronomy, they're like, what's the big deal? It's a big orange glowing donut. But the network of telescopes that had to work together to take this image, it was the equivalent of trying to photograph an image of an orange that's on the moon. It is like really, really small and far away. So it was a huge technological feat. So here in the very center, we have the shadow of the black hole, because even though it's a real image of a supermassive black hole, we unfortunately can't break the laws of physics. So the center of the black hole still remains black because no light can escape that region. The glowing region around it is what we call the accretion disk. And this means that this black hole is actively feeding. This is material, surrounding material, that's falling into the black hole. And as it's falling in, the different particles in the disk are actually rubbing together. So they're creating friction. And as we know, friction creates heat, which can then create light as well. So this is why this is glowing. The accretion disk material is rubbing against itself and glowing. And you can actually tell some interesting things about the black hole based on the fact that it's glowing more brightly on one side rather than the other. This tells us that the black hole is actually rotating on itself in a certain direction. So we've been thinking of and dreaming of this moment for a long time. In the bottom right corner here, you have what we had as a simulated image of a supermassive black hole with the accretion disk and the black shadow at the center. And it looks pretty similar to what we actually ended up taking. So that was great news. That means that our understanding and our physics of supermassive black holes as we know them are relatively true to nature. They're close to what is actually going on. So this is great news. The James Webb Space Telescope is another mission that's coming up soon that is going to be helping trying to understand black holes, including intermediate-sized black holes and supermassive black holes. So it's a really exciting mission, international mission headed by NASA, but with a strong contribution from the Canadian Space Agency, as well as the European Space Agency. There are 4 scientific instruments on it. Ours is called FGS NIRISS. It's a 2-for-1 deal. We have the guiding camera that allows all of the instruments to take super sharp images, and NIRISS, which is a scientific instrument. But I'll mention here specifically a program that will be using NIRSpec, which is one of the other instruments. And it's going to be able to help us weigh the mass of supermassive black holes much more accurately. So this is one example of the targets that James Webb is going to be looking at. It's a galaxy called NGC 4151. It's a bit of a boring name, so it has a nickname called the Eye of Sauron, which is much more interesting, I find. And NIRSpec, which is the instrument in the bottom corner here, one of James Webb's instruments, will be able to lay down a bunch of little slitlets on this observation in order to take 1,000 spectra, a spectra being when you take the light of an object and you break it down in its different colors in order to understand exactly what is going on at different wavelengths in the image. So 1,000 spectra in an area 1,000 light years across, and it's going to be able to measure the motion of the stars, just like we did with our own Milky Way, to measure exactly how heavy the supermassive black hole at the heart of this galaxy is. So James Webb will be able to do that for this galaxy, the Eye of Sauron, and for a bunch of other galaxies. So lots of stuff that we've done already has been like huge feats of technology. We know a lot about black holes already, but there's still a lot for us to find out. And a lot of it is going to rely on the technology that we create for the future as well. So I hope I've convinced you that black holes don't suck.
Thank you so much, Nathalie. That was amazing. So much to delve in here, and let's bring Rachel back in here as well, because we've got about 10 minutes left. But we're gonna try to knock off all the questions, and of course I'm monitoring on YouTube as well, so if he has some questions, so let's get right into it. And of course we can knock this one off fairly quickly, because you did sort of allude to perhaps what's on the other side of the black hole. We don't know yet, but what about this theory that there could be another universe on the other side of a black hole? You may want to delve into some of those theories.
Sure. So some people think that maybe it's like a tunnel to another dimension, be it a hell-like dimension or not. Have you seen Event Horizon?
Oh yeah.
Okay, yeah, it's a fantastic movie. And one of the scenes that is really great is Sam Neill, who's the scientist in the movie, explains that if you want to go from point A to point B, what's the fastest way? It's a straight line. No, it's not. If you can bend the piece of paper, like you're bending space-time, point A and B are simultaneously in the same spot, so you can like tunnel to another place in the universe instantaneously. So some people think that you can maybe transform a black hole into what we call a wormhole and use it to travel over large distances to another dimension, even through time potentially, but we don't have any concrete evidence that this is the case for the moment. It is a cool thought, and it is a great mechanism to use in science fiction movie, but no proof of any of this yet, unfortunately.
Yeah. Of course, with lots of wild claims that science fiction does give us, with great claims comes great extraordinary evidence that we do need.
Yeah.
But we can still hope, right? And I think we shouldn't. I think this is where science fiction is good for us, because it allows us to think about these things that we may not be able to figure out in our lifetime, but maybe years and years from now, maybe maybe someone will be able to figure out what's on the other side of a black hole.
That's right.
Let's get to another question from Sheila Smith. What will our galaxy look like when most of the stars reach the red giant phase? Who wants to tackle that one?
I can let you do that, Rachel, since it's stars.
Yeah, I'm not really sure though. Like, because that's very, very far into the future. And if we're saying that most of the stars in our Milky Way are kind of in that same sweet spot that our sun is on that main sequence, they will eventually undergo that red giant phase and eject all of that outer material and expand. But, you know, the space in between stars is kind of few and far between. So we don't have that kind of worry that we have a home like Earth really close to a star undergoing that red giant phase.
And of course, by that point, there will have been, you know, like new stars that will have born out over the course of that time, right? So it's not like, you know, all of the stars are just going to vanish, because there will be new stars to kind of replace them, right?
That's
Exactly.
right. Yeah, but there is a phase. So galaxies also evolve because they're made up of stars, and stars are evolving within them. So it's sort of like cells evolving within a larger organism. And so as galaxies get older and their stars inside get older as well, galaxies usually become what we call red and dead, where all of the gas that can be used inside of the galaxy to make new stars has been mostly depleted. So star formation doesn't really happen anymore. And then all of the really young stars have sort of like blown up and they're not there anymore. So all you have left over are very low mass red stars that are colder, and they are also redder. And one thing that's interesting about stars is when you're like sort of quiet and meek and small, you live a much longer life. If you're like big and loud and hot and brash, you like live a much shorter life. So you can end up finally just like getting rid of like the young hot heads, and then you end up with all the quiet red stars just sort of chilling out.
Whenever I hear like that phrase, you know, when they're talking about stars, live hot, die young, I have like the song in my head.
That's right.
I won't sing it. Next question comes from Edwin. Does a black hole have a finite amount of matter it can absorb, or will it keep growing in size and keep absorbing matter? That's a great question, Edwin.
As long as something is feeding the black hole, it will keep growing. So it just needs to have something within its event horizon or something in its accretion disk to keep feeding. So supermassive black holes, we think, happened in part because when galaxies collide and they have like a smaller supermassive black hole, the two supermassive black holes will collide together and then like eat each other and then become like a doubly supermassive black hole. So as long as there's like material around, they will keep growing. They have no appetite control.
Well, I think we're going to need another name for a doubly supermassive black hole. We need like another category if there's two supermassive black holes that are coming together.
Uber massive black hole.
Another question comes from Gabe. Is our sun potentially orbiting around a supermassive black hole too? So you did talk about the black hole inside of our galaxy. Is that classified as a supermassive black hole?
Yes, that's right. So Sagittarius A is a supermassive black hole, and all of the stars inside of our solar system orbit around that center. And our sun, which is about 2/3 of the way out in an arm of the Milky Way, as I mentioned, takes about 250 million years to do one full orbit around that supermassive black hole.
As I'm monitoring YouTube here, we got a question from Harry, which is a really interesting question, which I believe is talking about kind of like the similar question I asked you, Rachel, about, you know, how we measure the mass of stars. So how do we measure the mass of black holes? Like what are the characteristics, you know, determine some of that data that we get? Is it just looking at the stars that are orbit around the black hole? I guess this is more for Nathalie. Maybe.
This is for me. Okay, I wasn't sure. I didn't want to like jump in. Yeah, so it's relatively simple undergraduate physics that you can do. It's just Keplerian equations, and it's the same thing that you can do. You can measure the mass of the sun by looking at like how fast the planets are spinning around it, and like based on how far away they are. So if you're looking at the motion of stars, you can tell how massive whatever is within that orbit. And the same concept actually led to the discovery that dark matter exists, because people were looking at how fast stars were spinning around a galaxy, and they realized, well, there's a lot more stuff there than is bright. So there's like a bunch of matter that is dark in there, and we can see its gravitational effect, but not its light. So it's a very nifty equation that has like lots of different usages in astronomy.
I was going to say that question reminded me of a midterm that I had back in university.
Another question comes in from Natasha. You mentioned that replacing the sun with a black hole will not affect the gravitational force of the universe. So how much of an increase in mass would be needed so that gravitational force begins to be affected?
So it depends how sensitive you are, I guess, to a gravitational effect. As soon as you change the mass at all, you end up with like some gravitational effect. But if you're talking about like changing or like kicking out the planets, then it would have to be quite a bit bigger. I'd have to do some back of the envelope calculations to figure out what exactly. But as soon as you change the mass, even just a little bit, you do end up changing the gravitational effect. It might just be like a microscopic amount.
We're almost right out of time. We're going to try to get through as many of these questions as possible. But I do sort of like this question because one of my favorite movies is Interstellar, and this question goes into: can black holes be like a machine to travel time?
So as I mentioned, it is possible theoretically that maybe a black hole could be turned into a wormhole, and it wouldn't only allow you to travel through space, but also through time. This is where like the whole space-time concept comes in, because space and time are so interlinked together. And it's true that when you get close to a black hole, the way you perceive time versus the way someone who's like not near the black hole will perceive time will be affected by the by the gravity of the black hole. But we don't have any proof that we can like use a black hole to travel through time, but it does mess around with time. The part where they get close to the black hole and only like a few hours pass for them, but like a few decades pass for the other guy that stayed on the ship, that part is actually true.
I mean, that's just like crazy to think. Like, is there something that you could maybe conceive of? No, I can't see humans getting close to a black hole anytime soon. But is there something kind of like that we might be able to simulate even just like a little bit? Is there like an example of getting close to like a really large sun that we might be able to simulate some of this time travel that we see, maybe not on a grand scale, like years and years, but even like minutes maybe?
Well, like something really simple that I can mention is that astronauts who have spent a lot of time in the International Space Station, it's because they're farther away from the Earth, so they feel the Earth's gravity a little bit less. They will have like a change in their timeline of something like a few seconds, but like it accumulates over time. It's a very small change in the gravity that they perceive, but because they spend hundreds and hundreds of days sometimes in space, it can accumulate to like a difference of a few seconds in their lifetime versus someone who has stayed on the Earth the entirety of their lifetime.
Awesome. And let's go with another question, which is a question that I have been asking, and I asked you this very question earlier this year. What's taking so long for the new black hole picture to come out from the Event Horizon Telescope?
So it was actually in the plans to take a picture of Sagittarius A at the same time as M87, but there was bad weather, so the Event Horizon Telescope couldn't actually get a good image of it. Essentially, it is trying to link up all the data from 8 different telescopes, putting it together in the best way possible, and then doing the imaging correctly. It's not taking the observation that is taking a long time, it is analyzing the data that is taking a long time. It takes a lot of computing power and like really, really sophisticated algorithms to do it. So that is what is taking a long time right now.
Wow. Looks like we may have lost Rachel, but let's go through. We're going to go through some of these. Let's see if we can get Rachel back here and see how many
I think
more
I see
questions.
her.
Can you see her?
She popped back in.
Yeah, I can't see her. I can't get her video on though.
I'm here. I have audio, but I can't seem to start my video.
Okay, that's all right. Let's go with another question here. Ooh, do black holes interact with dark matter?
Do black holes interact with dark matter? They interact gravitationally, but dark matter is really rough. Dark matter is super abundant, but also not dense at all, in the sense that right now there is dark matter with you in the room, but it's like one particle of dark matter in the entirety of your room, and like we are submerged by like normal matter. But space is so empty of normal matter that on the scale of an entire galaxy, because dark matter is distributed everywhere, whereas normal matter is like very localized where it's bright, you end up with like a lot more dark matter. But dark matter is really hard to study because it doesn't interact a lot with anything. So dark matter will have a gravitational effect on a black hole the same way that it would have a gravitational effect on a star, meaning that the total mass of dark matter will make things spin around faster, but it won't necessarily collide with it and like start doing interesting stuff, because dark matter is hard to study because it weakly interacts with everything.
Do you think we are going to get any answers about dark matter anytime soon?
I do think so, and Canadians are at the forefront of this. We have Snow Lab, and they have lots of experiments, like giant spheres filled with liquid that are just trying to interact with a dark matter particle. So I do think I'm gonna say in the next 10 years we will have detected our first particle of dark matter.
Well, there you go. You heard it from Nathalie Ouellette herself. Thank you so much, Nathalie, for joining us and staying up late with us here on the West Coast.
Of course.
Rachel, thank you as always. We're going to be live on YouTube tomorrow at 2 o'clock if anyone wants to join. We're delving into the same topic, really, but probably we'll have a whole bunch of kids. So if anyone out there, has kids that don't want to stay up late, 2 p.m. Pacific time is when we're going to be on YouTube. And of course, to everyone out there, I'm so sorry for everyone that was on YouTube. They couldn't get into the Zoom. We'll fix this for the next time. We're going to do more of these Cosmic Nights. Please fill out the survey that we're going to send out to everyone. We're also going to put a link to that interview that I did with Daryl Haggard. She worked on the Event Horizon Telescope, so make sure to watch that bonus coverage. And of course, please donate to us. You can go onto our website and find the Donate Now button. We really appreciate it. But for me, Michael, from my kitchen, thank you so much for joining Cosmic Nights. We'll see you again next time.
Bye.